In the last video, we went over various rules for differentiation. And just as kind of a review for what we had there, remember when we differentiate a constant function, we always get 0. When we differentiate a power of x, we're able to bring down that power as a coefficient in front and reduce the power by 1. When we have a multiple times a differentiable function, we can differentiate that multiple by just multiplying the derivative of the function by that same multiple. And finally, when we have the sum or difference of two functions that are differentiable, we can just take the sum or difference of their derivatives to get the derivative of the sum or difference. So you might want to remember this page or write those down for yourself. They're definitely very important rules that we'll be using very often. In fact, we'll constantly be using these throughout this course. So get very familiar with these rules. But what we're going to do in this video right now is put these rules to work, show how they're used in various problems. I'm going to start off with problem 14. So our function here is g of x. They decided to pick a name other than f, but that doesn't change what we're going to do with it. G of x is equal to 3x squared plus 5x cubed. We have a polynomial here. And when we differentiate this thing, don't be afraid to overuse parentheses, at least until we get very used to how all this works. So I'm going to take the derivative. Remember from our rule for addition, the sum of these two functions can be handled directly, or we can handle each term separately, basically. So this 3x squared, I'm going to differentiate that, and I'm also going to differentiate 5x cubed, and I'm going to add the results together. Next, because I know how to differentiate powers, we have a power rule, but we don't want to deal with the constants that are in front of them. We can pull those constants out. So this is 3 times the derivative of x squared. And this one is 5 times the derivative of x cubed. Finally, we put our power rule to use. Remember here, this is x to the power 2, so we bring that 2 out in front, and reduce that 2 by 1. So 2 becomes a 1. Of course, here x to the 1 is just an x. Over here, this time our power is 3, so we bring that 3 out, and now we reduce the 3 to a 2. And so we can now multiply these together. We have 3 times 2, that's a 6 as a multiple for x. And we also have 5 times 3, which is 15 times x squared. So the derivative of 3x squared plus 5x cubed is 6x plus 15x squared. And we didn't have to take any limits there whatsoever. A lot nicer to do it this way. Next is problem 18. This time they don't actually name the function. We're just going to say that y is equal to 2x cubed minus x squared plus 3x minus 1. So we actually have 4 terms in this problem. But it doesn't change the way that we handle it. We still have a sum or difference of various terms, and so we can take that apart as a sum or difference of their derivatives. But I'm also going to go ahead and combine the step where I pull out our constants. So here, when I differentiate 2x cubed, I have 2 times the derivative of x cubed. For minus x squared, I'm subtracting the derivative of x squared. There's no constant to pull out there, unless you include the negative 1 as a constant. You can treat this as plus a negative x squared, if you wanted to. Now we have 3x. We're adding the derivative of that. Of course, we could pull out that 3. So 3 times the derivative of x. Then finally, minus the derivative of 1. Derivative of x cubed, we actually just did that on the previous page, but just it's easier just to remember the power rule than having to memorize a whole bunch of different rules for various functions. Aside from maybe x squared and x, because those are nice and easy enough. But x cubed, I pull out that 3. I reduce the power to a 2. For x squared, I bring down that 2, and I reduce the power by 1. Of course, here, x to the 1 is x. For x, we can treat this as x to the first power. So we can say that we bring down the 1, so we have 1, and we have an x to the 0th power. Of course, x to the 0th power is a 1 as well, so really, we're just multiplying by 1. And keeping in mind that x to the 0th is 1 may be something that might trip you up a lot, so if that does trip you up, just remember that the derivative of x is equal to 1. Finally, the derivative of 1, well, 1 is a constant. So that's just 0. That's always equal to 0. And so what we have here, we have a 6x squared. We saw a minus 2x. Of course, everything that the 3 is being multiplied to is a 1, so we just end up with that 3. Of course, the 0 goes away. So the derivative of this cubic is this quadratic. Moving right along, let's look at problem 23. This time, our function is 4x to the minus 2 power plus 2x squared. So this is not a polynomial, because we have a negative power for this x. But that doesn't actually change anything about our process, because our power rule works for any power of x, not just positive integers. So we can just do exactly what we were doing before. We pull out those coefficients, take the derivatives of those powers. So here, 4x to the minus 2, we take the 4 out, we differentiate x to the minus 2. We take the 2x squared separately, so we add plus 2 times the derivative of x squared. Derivative of x to the minus 2, the power here is minus 2, so we pull out a minus 2, and then we subtract 1 from our power. Remember here, negative 2, when we subtract 1 from it, doesn't become smaller, it actually becomes a more negative number. We actually get a negative 3 for the new power. Then we have plus 2 times the derivative of x squared. Hopefully by this time we've gotten quite used to x squared becoming 2x when we differentiate it. But again, that is just an example of our power rule at work. And of course we can go ahead and multiply these out. 4 times negative 2 is a negative 8. Still times x to the negative 3. And then this becomes a plus 4 times x. In problem 41, we're going to return to looking at a polynomial. We have f of x is equal to 2x cubed plus 8x squared minus x minus 4. But this time, they are going to give us a point. So they're claiming that negative 1, 3 is a point on this curve, if we were actually plot out this cubic function. And they want us to differentiate this function and then use the derivative to talk about the slope of the function at this given point. In fact, we're going to go a step further and find the tangent line at that point. So the first thing we do is differentiate. So derivative of f, we get to differentiate each term separately. We start with the 2x cubed. Where we get to take 2 times the derivative of x cubed. I'm not going to write out the d dx every time. Hopefully you'll get used to just kind of smoothly going through this as we go. But the derivative of x cubed, remember by our power rule, is 3x squared. Bring down that 3, reduce the 3 by 1 to get a 2. Then we have 8 times the derivative of x squared is 2x, for the similar reasons. Minus the derivative of x is 1. And then minus the derivative of 4, which is 0. Derivative of a constant is 0. In other words, our derivative here is 6x squared plus 16x minus 1. At the point negative 1, 3, we're saying that x is equal to negative 1, so we're really going to plug negative 1 into our derivative. Basically, we're plugging in negative 1 for all the x's. So 6 times negative 1 squared plus 16 times negative 1 minus 1. This is it's actually a positive 6. Actually, let's write this down here. It's a positive 6 because the negative 1 squared is a positive 1. Then we have a minus 16 and a minus 1. And that all comes out to be a negative 11. Let's go ahead and plot this. So our function, f of x is equal to 2x cubed plus x squared, plus 8x squared minus x minus 4. This is our curve. It starts out low, goes up high, and then comes back down a little bit. And they claim the point negative 1, 3 is on the curve. And it definitely looks like it's on the curve. And what we got, our result there, was saying that the slope of our curve at this point is negative 11. Now you could try to figure out exactly if that makes any sense to you, but when we actually plot our tangent line, it'll make a lot of sense. So let's actually find the tangent line at that point. We have a point on the line, and now we have the slope. This is our slope, for our tangent line. So we can use what we call the point slope form. Basically, we take y minus our y value here being the 3, is equal to our slope of negative 11 times x minus our x value here being a negative 1. I'm going to go ahead and move stuff around here. For one thing, I'm going to distribute the negative 11. We get a negative 11 times x, but then we have a plus 1 that's being multiplied to negative 11, which means we get a negative 11 too, as our second part there. But then this 3 that I have over here, I'm going to move over to the other side. So I'm going to add 3 to the other side. Well, we have a y equals negative 11x, but then the negative 11 and the 3 will combine to give a negative 8. So our y-intercept of this tangent line should be negative 8. Obviously, the negative 11 we already knew from the slope. If we go ahead and plot this line, y equals negative 11x minus 8, it definitely does pass through our point A, and it really does agree with our graph around that point. This is, in fact, the tangent line to this curve at that point. Now, if you look a little bit closer, you can actually see that it is actually below the curve down here, but then it comes up and actually intersects it again up here. This is an example of a place where tangent line does actually intersect the curve at another point. It's a little hard to tell just because it actually agrees so closely for so long. But the point here is that this does represent the slope of our graph at that point. And we didn't have to take any limits to find it. Moving on to problem 44. This time our function is 3 times the quantity 5 minus x squared. This is in the same category of what we did in the last one. They're going to give us a point of 5, 0. They're claiming that's a point on our curve. and we want to find the tangent line, or at least talk about the slope and all that, at that point. Note that this is a polynomial. This is a quadratic, in fact. But because the 5 minus x is inside the square, this is not just a simple polynomial that we did in the last example. There we actually had completely separate terms that were all a coefficient times the power of x. Here we have something that's not just x in the square, and that's a slightly different kind of situation. We will get a rule later in section 2.5 that will allow us to tackle this quite directly, but for the moment what we need to do is expand this out. We need to put this as a sum or difference of various terms that are a coefficient times a power of x. If we don't do that, we can't use our rules as we have them right now. So I'm going to go ahead and I'm going to expand out 5 minus x squared. That becomes a 25 minus 10x plus x squared. So here, basically, the 25 comes from 5 squared. The 10 comes from 2 times 5 times negative x. That gives us a negative 10x. And then finally, the x squared here comes from the negative x squared. Finally, I'm going to take this 3 and I'm going to distribute it. So 3 times 25 is 75. 3 times negative 10x is negative 30x. And 3 times x squared is, of course, just 3x squared. Now, this is a function we know how to differentiate. This is a very nice polynomial, nice quadratic. And we can differentiate term by term. We have the derivative of 75, which is 0. We have the derivative of negative 30x, which means we take negative 30 multiplied by the derivative of x, which of course, by this point you should be aware that's going to be a 1. And then finally 3 times the derivative of x squared, which is a 2x. So ultimately here we have, I'm going to go ahead and put the 3 times 2x, or 6x first. Then I'm going to put the minus 30. Just because I don't like putting the negative term first. Of course, the 0 goes away. So the derivative of this thing, of this 3 times the quantity 5 minus x quantity squared, is 6x minus 30. Of course, we are putting this point into our function. So we're really looking at what is the slope at x equals 5. I'm going to go ahead and plug 5 into our formula here. 6 times 5 is 30. 30 minus 30, of course, is 0. So we have a situation where our slope of our tangent line is 0, and it's at the point 5, 0. Of course, the slope of a line that has slope 0 is a horizontal line, and the horizontal line is given by what y values are on it. So we're really just looking at the horizontal line y equals 0. But this also has another name. This is the x-axis. The x-axis itself is the tangent line to this curve at that point. And in fact, if we go ahead and graph it, so it's 3 times 5 minus x squared. If you look at the point 5, 0, it's actually at our vertex of this parabola. And hopefully it should be rather clear that our x-axis is just going to be our tangent line there. It is just barely touching at that point. Of course, it doesn't really completely agree with the graph of our parabola, because the parabola is actually turning the most it ever turns at its vertex. But this is the closest approximation to our curve at this point, using a line specifically. Next up, let's look at problem 47. This time our function f of x is equal to the cube root of x plus the fifth root of x. And specifically, they want us to look at the point 1, 2. Let's go ahead and plot this right away this time. So our function is the cube root of x. I'm actually going to use fractional powers there. Same thing here. We have the cube root of x plus the fifth root of x, and we get this curve here. Actually, if you think about it, it looks like we should have a vertical tangent line at 0, so it's probably not differentiable there. But that's not what we're looking at. We're looking at the point 1, 2. It's this point up here. And we want to find out what is the actual tangent line at that point. That question is not really obvious until we actually find that derivative. So we want to differentiate this function, keeping in mind, like I already showed you, that we can turn the cube root of x into the power x to the 1/3, and the fifth root of x is x to the 1/5. That's what fractional powers mean. When we differentiate this thing, the derivative of x to the 1/3 power, we take that power of 1/3, bring it out in front, and then we reduce the power by 1. So 1/3 minus 1 is negative 2/3. For x to the 1/5, we bring down that 1/5. Then we take 1/5 minus 1. 1/5 minus 1 is a negative 4/5. And we could just leave it like this. Or if you prefer, we can just, at least for some practice, we could go ahead and rephrase this. Remember, the negative powers on here means that both of these turn into powers of x on the bottom, in the denominator. So x to the 2/3, the third part of that becomes a cube root, and then the square part of that, the 2 there, becomes a square. So this term here is 1/3 times the cube root of x squared. This one becomes a 1/5 times the fifth root of x to the 4th. Again, the minus sign means it's on the bottom, the fifth here means it's the fifth root, and the 4 here just means it's the 4th power. Now, if you want to, you could also rephrase these as the square of the cube root of x, or the 4th power of the fifth root of x. Which one, whether or not the 4 is on the inside or the outside is not too important here. But of course, the main thing that we want to know is what happens at 1, 2. And 1 is actually a pretty easy number to plug in. That's why they chose that one. If we plug in 1 here, we have 1/3 times 1 to some power, but 1 to any power is just 1. And we have 1/5 times 1 to some power, but again, it's just 1. 1/3 plus 1/5, going to have to combine the fractions there. Turns out we get an 8/15. So the tangent line through this point has a slope of 8/15. We can then use the point slope form to get the equation of our tangent line. We have y minus our y value of 2 is equal to our slope of 8/15 times x minus our x value of 1. I'm going to go ahead and, again, move stuff around until this is in our slope-intercept form. That means I get to distribute the 8/15 both to the x and to the 1. I take the minus 2 that's over here, and I add it to the other side. Then I get to combine the minus 8/15 and the 2. Everything else just stays as it is. Our slope is still 8/15. But now we get our y-intercept of 22/15. And if I go ahead and plot that line, I get my tangent line at A, exactly as I expect to get it. Of course, it does hit our graph at another point, but that's not important. We're concerned more about what's happening at A than we're about anything else. So this is the line that approximates our curve as closely as possible for a line at that point. let's move on to problem 57. In this problem, we're just going to be differentiating. We're not going to find tangent lines. So if you want to try your hand at it, go right ahead. Pick some value of x, and you can plug it into the function and get a y value. But we're not going to do that right here. So our function here is x times x squared plus 1. This is the product of two polynomials. X itself is a polynomial, and of course we have the quadratic x squared plus 1. We don't have a rule for how to handle products right now. We'll actually get a general rule for products in section 2.4. But since we're just dealing with two polynomials, we can go ahead and just expand this. We can distribute the x to both of our terms. This polynomial here is just x cubed plus x. So x times x squared and x times 1. So we can differentiate this thing. In fact, this is actually a relatively easy one to differentiate. We differentiate the x cubed separately from the x. Derivative x cubed, remember our power rule, we bring down that 3, and we reduce the 3 by 1 to get a new power of 2. Same thing for the x, but it's easier just to remember that the derivative of x is equal to 1. So there's really not a lot to this, but we couldn't tackle it until we did this expansion. We can't really tackle this directly at this point. In fact, even when we get a rule for products later on, this is probably the easier way of handling it. That rule's more for cases where we can't do this expansion. '59 is actually pretty similar, except a little bit different in some ways. We have a polynomial of 2 times x to the cubed minus 4x squared plus 3. But now, instead of multiplying by something, we're going to divide by something. We're dividing by x squared. And just like the previous problem, we don't have a rule for dealing with quotients. We're going to actually get a general rule for quotients in 2.4. But here, because we are just dividing by a power of x, this x squared, and not by some polynomial with more terms in it, if this was x squared plus 2, then I wouldn't be able to do this right now. We'd have to wait until we get to the quotient rule in a later section. But because we're just dealing with dividing by x squared, we can actually just split this up into multiple fractions. I'm going to write this as this first term of 2x cubed divided by our x squared. Then we have a minus 4x squared over x squared. And then we have the 3 over x squared. You're allowed to do that. In fact, this is probably the easiest way to tackle this. Of course, we can simplify these. For instance, x cubed divided by x squared is just x. So this first term is really just 2 times x. Here, the x squareds actually completely cancel each other out. We're just left with the 4. So we have a minus 4. This time there's no x's on top, so we can leave that as a 3 over x squared. But if we want to do anything with differentiation and our power rule, we want to express this 3 over x squared as a power of x. We can't just differentiate the x squared on the bottom directly. This we have to actually rephrase as a power of x on the top. If we don't do that, we can't use the power rule. So leaving the 2x minus 4 alone, we're going to convert this into a 3 times x to the minus 2 power. So make sure you take these powers of x that are on the bottom and turn them into x to a negative power, or else you're going to get the wrong answer. But once we do that, we can differentiate pretty easily, just following our rules that we've been doing over and over again. So we have the derivative of 2x is 2 times the derivative of x, which is 1. So I'm just going to leave that as a 2. Derivative of negative 4, again, this is a constant, So the derivative of that is 0. I'm just going to completely leave that out. I'm not even going to write it. And then finally, the one that's actually going to be a little bit more interesting is this 3 times x to the negative 2. We end up with that 3 times the derivative of x to the negative 2. We're going to use our power rule there. And our power is negative 2, so we bring down that negative 2. And then we subtract 1 from our power. But remember, this is a negative, so negative 2 minus 1 is a negative 3. Of course, we can then go ahead and multiply the 3 and the negative 2 that we have here to get a negative 6. So 2 minus 6 times x to the negative 3. And if we don't want to have the negative power in here anymore, we can now go ahead and do the opposite of what we did over here with the x squared on the bottom and turn this into an x cubed on the bottom. So this is really 2 minus 6 over x cubed. That's probably the way I'd like to write it, if given the option. So just be aware that some of these problems are going to require you to do a little bit of algebra in order to get it into a form that we can actually use our rules on. So you want to pay attention for that. Don't just try to blindly use the rules in various places. Like, you don't just try to differentiate the top and differentiate the bottom. That actually does not work, and we'll see why in 2.4. But the moral of the story is that derivatives can be really easy if we can turn the function into the sum or difference of powers of x with coefficients in front of them. Unfortunately, we can't do that with every function, but we will get more, again, referencing these rules that we're going to get in 2.4 and 2.5, and we'll be able to do just about any function that we can work with for now. We'll later in I think it's chapter 4, we'll start talking about exponentials and logarithms. We'll have rules for those that we come across at that point too. But once we get those rules in 2.4 and 2.5, we'll basically be able to tackle any function we can work with at this time. But because these rules in this section are so fundamental, I strongly suggest work out a bunch of the problems in this section. Just keep doing more problems until second nature, because we'll be using these rules constantly, and practice does make perfect. So make sure these are ingrained in your mind. But I'm going to leave this video here, and I'll see you guys next week.